Today we're here to talk about free fall. Free fall is simply vertical linear motion. Up to this point in time, what we've been talking about is horizontal linear motion. Things that move around along the ground, they move in the horizontal direction parallel to the Earth's surface. Here we're going to start talking about things that move vertically in relationship to the Earth's surface. So free fall. Just stop for a moment and think, what do you know about objects that take and that fall? Okay, objects that are falling through the air. How about objects that are tossed straight up? Okay. One thing that's really important to remember in here is that we always neglect air resistance. Okay, so every situation that I'm giving you, unless we're talking about terminal velocity, which will be coming up soon, we're always going to just simply neglect air resistance.
Aristotle, one of the greatest of the ancient Greek thinkers, believed that heavy objects fell to earth faster than lighter objects. Drop a stone and a feather at the same time and watch which one reaches the ground first. For almost 2,000 years, Aristotle's belief about falling things was accepted as fact. In the early 17th century, an Italian named Galileo wondered if it was true. Legend has it that an assistant climbed to the top of the Leaning Tower of Pisa and dropped 2 stones of differing weights, while Galileo stayed on the ground to observe what happened. He found that both stones hit the ground at exactly the same time. Whether Galileo actually dropped stones from the Tower of Pisa or not, he tested his idea by experimentation and observation, a process that is fundamental to science. For this reason alone, he is often credited with being the father of science.
Okay, free fall acceleration is caused by gravity. Gravity is an acceleration that is always taken and is always pointed down, is pointed towards the center of the Earth. And it is 9.8 meters per second squared, or if we're in the customary system, it's 32 feet per second squared. These are 2 numbers that you do need to take and you do need to memorize.
All the motion we've talked about so far has involved cars on roads, carts on hills, planes in the sky, and so forth. But linear motion also includes objects that are falling. And that's the topic of today's lesson, falling objects.
During this lesson, you will state the law of falling bodies, determine the value of g, acceleration due to gravity, and solve motion problems involving free-falling objects.
Okay, we've all seen that objects accelerate as they fall. But studying this motion over the years has been confusing. The great philosopher Aristotle thought that heavier objects fall faster than lighter ones. That's because he could see a heavy object, like a hammer, falling faster than a light one, like a feather. See? But Aristotle was not a scientist and stopped there. In the early 1600s, Galileo Galilei studied the motion of falling objects. Legend has it that he dropped cannonballs of different sizes off the Leaning Tower of Pisa. But there is no evidence to confirm this. But we know that he did perform experiments, making use of a creative technique of imagining what would happen under ideal conditions. In the case of falling objects, the ideal condition would be the absence of air.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery.
objects are rather compact and fall a relatively short distance, we can say that they all accelerate the same. Look at these two falling rocks. It's obvious that they are not in a vacuum, but we can say that they both fall with the same constant acceleration. We say that objects falling with negligible or no air resistance are in free fall. The acceleration of objects in free fall is a constant. The sports term free fall is not the same as free fall in physics. To skydivers, free fall means falling without an open parachute. In this situation, air resistance is not negligible, but essential. It keeps the skydivers from accelerating as fast as objects do when air resistance is negligible. Don't get the sports term and the physics term confused.
Okay, so the equations that we're going to use for free-falling objects look a lot like the ones that we use for linear motion. I have 3 of them here, but if you'll notice, we've taken and we've replaced the A with a G. The G just simply stands for gravity. And the way these are written, gravity is assumed to be going down, but I've made a switch from years in the past, and we're going to try to call gravity positive. So the downward direction would be the positive direction, and then the upward direction would be the negative direction. So we'll see how that goes for this year. So again, here's your 3 equations. All we've done is simply switch the acceleration, the A, to a G, which stands for gravity, and that value will always be 9.8 meters per second squared, or 32 feet per second squared. All other equations that we used prior to this unit still work for objects that are not under the influence of gravity. In other words, everything we know is under the influence of gravity, but they're not the ones that are causing the motion, like a rolling ball, a car, anything that's moving horizontally. The effect of gravity is balanced by something called the normal force, so we can ignore it for right now.
Galileo performed experiments to measure the rate at which objects fall to Earth. Thanks to Galileo, we now know that the Earth's gravitational force causes an object to accelerate at a rate of approximately 9.8 meters per second squared. In other words, the object's velocity increases 9.8 meters per second for each second the object remains falling to the ground. Acceleration due to the Earth's gravity is represented by the symbol G. So that's it. You already know that the slope of a velocity versus time graph represents acceleration. When air resistance is negligible, all objects fall with the same constant acceleration. We call this constant acceleration due to gravity. For most places somewhere, the value of this acceleration due to gravity, given the symbol G, is 9.80 meters per second squared. So our experimental value of 10 meters per second squared was quite close. In fact, I'd say that within bounds of experimental error, it was the same. When objects are in free fall, we can use
dropped from a bridge. What is the velocity of the rock after it has fallen for 3.7 seconds? In this problem, we know time equals 3.7 seconds. Initial velocity is 0, and acceleration due to gravity is 9.80 meters per second squared. And we want to know final velocity. For this problem, we'll use an acceleration equation number 1, starting at rest. We don't need to do any rearranging. All we need to do is plug and chug. Plug in the numbers, and the answer is 36 meters per second.
Let's make the last example problem a little more difficult for those of you who need a challenge. What if the rock is thrown down at a velocity of 11 meters per second? How will this affect the acceleration at final velocity after 3.7 seconds? Your teacher will pause the tape and give you the information again. After you come up with your answers, come back and we'll go check it out.
The time in this problem is the same, 3.7 seconds. The only way this problem differs from the last is if the ball has an initial velocity of 11 meters per second in the same downward direction. Now, how will this affect the acceleration of the ball? Did we trick you? The answer is that once the ball leaves the person's hand, it's in free fall, so the acceleration does not change. It's still 9.80 meters per second squared. To find final velocity, we'll use equation number 1 with initial velocity included. Plugging in the numbers gives us the answer, 47 meters per second.
Okay, so I have another example here. A pebble is dropped from a bridge and hits the water 0.5 seconds after it's released. What height was the pebble dropped from? So again, just like one of the other examples earlier, and it just gives you another possibility here. Example 2, a care package is dropped out of a flying plane at 5,000 feet. How fast is the package going when it strikes the ground? And example 3, a baseball player hits a fly ball to the height of 50 feet. How much time does the fielder have to get into position to catch the ball? We're done.